A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
My Weird Prompts is a community-driven initiative exploring how AI can fuel curiosity and uncover the fascinating ways our world works. GPU compute for this podcast is generously provided by Modal. Learn more at modal.com.
You know, Herman, living here in Jerusalem, we have a very specific, almost visceral relationship with the sound of a siren. When that rising and falling tone of the red alert hits, it is not just a noise. It is a trigger for a massive, multi-layered sequence of events that has to happen in seconds. It is probably the most high-stakes notification system on the planet. You hear that sound and you know that somewhere a radar has locked onto a projectile, a trajectory has been calculated, a geographic polygon has been defined, and a signal has been sent to your specific neighborhood siren and your phone. All of that happens in less time than it takes most people to unlock their mobile device.
Herman Poppleberry here, and you are exactly right, Korn. It is the ultimate real-world test of what engineers call a mission-critical alerting pipeline. Our housemate Daniel actually sent us a fascinating prompt about this today. He was asking how these massive, life-critical systems like the Red Alert or Japan's earthquake warnings actually work under the hood. Specifically, he wanted to know how those architectural patterns translate to the kind of work developers are doing every day with automation tools like N8N or Zapier. It is easy to think of these as government magic, but when you peel back the layers, they are built on the same logic of webhooks, pub submodels, and data validation that we use in our own software stacks.
It is a great question because I think we often treat our own alerts as an afterthought. We set up a webhook, it pings Slack, and we'll call it a day. But when you look at how a system like the Common Alerting Protocol or Japan's J-Alert is built, you realize that a notification is just the tip of the iceberg. The real magic is in the infrastructure that ensures that message actually arrives when the network is screaming and the power is out. Think about the speed of J-Alert. It takes mere seconds from the moment a seismometer detects a primary wave to the moment a bullet train starts braking. That is not just a notification. That is a distributed system performing a physical action.
And today we are going to deconstruct that. We are going to look at the anatomy of these workflows, the trade-offs between speed and confirmation, and some really cool industrial standards like the ISA 18.2 for alarm management. We will even touch on how these systems cross air-gapped boundaries using hardware-level data diodes. It is basically infrastructure as code, but for the physical world where the stakes are life and death. We are moving beyond the hello world of notifications and into the 5 nines of mission-critical reliability.
I love that framing. Let us start with the basics then. When we talk about the alerting surface area, we are moving way beyond a simple push notification on a phone. We are talking about sirens, radio broadcasts, television overrides, and even automated industrial shutdowns. Herman, what is the connective tissue here? How do all these different devices, built by different manufacturers over different decades, speak the same language?
The industry standard, the lingua franca if you will, is something called the Common Alerting Protocol, or CAP version 1.2. It is an extensible markup language-based standard, or XML, which might sound a bit old school to developers who are used to JavaScript Object Notation, or JSON, and gRPC. But there is a reason it is XML-based. It is incredibly structured, highly extensible, and designed to be platform independent. When FEMA in the United States or the Homefront Command here sends out an alert, they are essentially publishing a CAP message to a central hub.
Why stick with XML though? If I am building a modern microservice in 2026, I am reaching for JSON every time. Is it just legacy momentum? Or is there a functional reason why the Federal Emergency Management Agency and other global bodies insist on this format?
It is about the schema and the strictness of the validation. In an emergency, you cannot have any ambiguity. You cannot have a field that might be a string in one version and an integer in another. The Common Alerting Protocol provides a rigid digital template for exchanging emergency alerts. It includes specific fields for the urgency, the severity, the certainty, and the geographic area defined as a set of coordinates. Because it is XML with a very strict schema, any system, whether it is a giant mechanical siren from the 1970s or a digital highway sign from 2024, can parse that payload and know exactly what to do without needing a complex application programming interface negotiation. It is the ultimate standardized webhook payload. It is designed to be read only. In many cases, meaning the device doesn't need to ask questions, it just executes based on the validated tags.
That makes sense. It is about interoperability across decades of hardware, but it brings up a bigger point about the difference between a notification and an alert. To me, a notification is informational. It is my phone telling me someone liked my photo or that my food delivery is 5 minutes away. An alert, especially a mission-critical one, implies an immediate need for action. It is a state change, not just a message.
Right. And that distinction changes the entire architecture. In a standard information technology environment, like a web server, we often prioritize throughput. We want to handle as many requests as possible. But in operational technology, or OT, which covers things like power plants, transit systems, or national defense, the priority is deterministic latency. We do not care if the system can handle 1 million messages a minute if it cannot guarantee that one specific alert will arrive in less than 200 milliseconds every single time, even under peak load. In IT, we use best effort delivery. In OT, we use guaranteed delivery, often at the expense of everything else.
That is a huge shift in mindset. It reminds me of what we discussed back in episode 745, where we looked at why cell broadcast is so much better than an app for these situations. If you are building an automation in NATN, you are probably using a standard hypertext transfer protocol post request to a webhook. But in a massive emergency, that model breaks down because it relies on a one-to-one connection.
It really does. Think about the thundering herd problem. If you try to send a standard short message service, or SMS, to 10 million people at once, the cellular towers will fall over. The signaling channels just cannot handle that kind of concurrency because each message requires a session, a handshake, and a confirmation. This is why the Wireless Emergency Alert System, or WEA, uses cell broadcast.
For those who missed that episode, can you give us the quick technical breakdown of why broadcast is the superior architecture for mass alerting?
Sure, a standard text message is a point-to-point connection. The network has to find your specific device, establish a session, send the data, and wait for an acknowledgement or an ACK. In a cell broadcast, the tower just yells the message to every device within its radius on a specific frequency. There is no session, and there is no acknowledgement. It is a pure fan-out pattern. The tower does not care if you received it. Its only job is to blast the data out. This is why you will see your phone get an alert even when the network is so congested that you cannot send a regular text or make a phone call. It is the difference between trying to call 10,000 people individually to tell them the building is on fire versus just pulling the fire alarm.
So we are sacrificing the confirmation of delivery for the guarantee of the broadcast. That seems like a classic architectural trade-off. If I am a developer building a critical system, how do I decide between a model that requires an acknowledgement and one that just fires and forgets?
It depends on the cost of failure. If the cost of the network clogging up is higher than the cost of a few people missing the alert, you go with broadcast. But inside a data center or a factory, you usually want that acknowledgement. This is where we see the transition from information technology to operational technology. In a factory, if a sensor detects a gas leak, the alerting system will use a pub-sub model, or publish-subscribe, where the alert is published to a broker like MQTT or RabbitMQ. Multiple subscribers. The siren, the ventilation system, the emergency shutoff valve all grab that message. In that environment, you want each of those subscribers to send an ACK back to the broker to prove they have taken action.
And in those closed systems, you can actually implement much more sophisticated retry logic and dead letter queues. If the ventilation system does not acknowledge the turn on command within 50 milliseconds, the alerting broker can immediately escalate that to a secondary system or a human operator. But here is something that has always fascinated me, Herman, the security aspect. How do you get an alert from a highly secure, classified, or air-gapped network out to the public, or even to a less secure monitoring station, without creating a giant hole for hackers.
That is where hardware-level data diodes come in. This is one of my favorite pieces of hard engineering. Imagine a physical piece of hardware that only allows light to travel in one direction through a fiber optic cable. It is physically impossible for data to flow back the other way because there is no receiving laser on the other side. So, you have your mission-critical, secure network on one side. It sends the alert payload through the diode. The unclassified network on the other side receives it and pushes it to the public webhooks or the cell towers. There is no digital handshake, no return path for a hacker to exploit. It is a one-way street guaranteed by physics.
That is incredible. It is the ultimate firewall. I think developers can learn a lot from that one-way philosophy. Even if you are just using a cloud-based automation tool, thinking about your data flow in terms of unidirectional segments can prevent a lot of cascading failures. If your alerting system can trigger your production environment, but your production environment has no way to talk back to the alerting core, you have created a very resilient safety gap. You have essentially isolated the brain of the system from the muscles.
Now, let us look at a real-world example of this in action, because this is where the automation gets really cool. Japan's J-Alert system is probably the gold standard for this. It uses a network of 4,235 seismometers across the country. When an earthquake starts, it detects the primary waves, or P waves. These are fast-moving, low-frequency waves that don't do much damage, but travel much faster than the destructive S waves, or secondary waves, which cause the actual shaking.
Right. The P waves are basically the heads-up signal from the Earth itself. It is like the Earth is sending its own CAP message before the disaster arrives.
Precisely. And the J-Alert system is designed to trigger automated actions within a 5 to 30-second window before the heavy shaking starts. This is not just about sending a tweet or a push notification. The system is hardwired into the national infrastructure. It automatically triggers the braking systems on the Shinkansen bullet trains. It commands elevators to stop at the nearest floor and open their doors so people do not get trapped. It even shuts off gas lines to prevent the fires that usually follow big quakes. This is machine-to-machine automation at its most critical.
That is the key insight for our listeners who are into automation. The notification to the human. The "hey, an earthquake is coming" is almost secondary. The primary goal is the machine-to-machine automation. If you are building a system that monitors your server health, don't just send yourself a Slack message when the disk is 90% full. Build the automation that spins up a new instance or clears the cache first. The alert should be a report of an action taken, not just a cry for help.
That is such a pro-level tip, Korn. We actually talked about something similar in episode 888 when we looked at the engineering behind modern sirens. They are not just loud horns anymore. They are intelligent nodes in a distributed network that can perform self-diagnostics and report back their status. And when you look at the financial world, you see the same patterns. Look at the New York Stock Exchange and the Securities and Exchange Commission rule, ADB. These are the market-wide circuit breakers.
Oh, I remember that being a huge topic during the market volatility back in April 2025. People were shocked at how quickly the entire market just stopped. It felt like a glitch, but it was actually the system working perfectly.
It felt like the world froze, but it was just a massive, automated alerting pipeline doing exactly what it was designed to do. The architecture is a series of thresholds. If the Standard & Poor's 500 index drops 7%, that triggers a level 1 halt. The price feed hits a threshold, a signal is published to a high-speed bus, and every trading engine in the world has to acknowledge that halt signal and stop executing trades for 15 minutes. If it drops 13%, that is a level 2 halt. If it hits 20%, the market shuts down for the day.
And that is all happening at the level of microseconds, right? There is no human in the loop saying, should we stop today?
No way. By the time a human could even process the numbers, the damage would be done. It is a purely automated circuit breaker. And this brings us to a really important concept for anyone building these kinds of systems, alarm rationalization. This comes from a standard called ISA 18.2. It was originally developed for the process industries, think oil refineries and power plants, to prevent what they call alarm floods.
I have definitely experienced a digital version of an alarm flood. You have one small database error, And suddenly, your phone is vibrating off the table with 500 different notifications because every single microservice is screaming that it cannot connect to the database. You end up ignoring all of them because you can't find the signal in the noise.
That is exactly what ISA 18.2 is designed to stop. In a refinery, if a main power bus fails, you might get 10,000 alarms in a single minute. A human operator cannot possibly process that. Alarm rationalization is the process of defining which alarms are actually actionable and prioritizing them. It involves things like alarm shelving, where you can temporarily silence a nuisance alarm that you are already aware of, so it does not drown out a new, more critical problem. It also involves alarm suppression, where if System A fails, you automatically suppress all the secondary alarms from Systems B, C, and D that rely on System A.
That sounds a lot like how we should be managing our dead letter queues in a message-driven architecture. If a message fails, you do not just want to retry it forever and clog up the system. You move it to a separate queue, you alert the admin once, and you let the rest of the system keep moving. It is about protecting the consumer of the alert, whether that is a human or another piece of software.
If you are using N8N or Zapier, you should be building in logic that says, if I have already sent this alert in the last hour, do not send it again. Or, better yet, aggregate all these small errors and send me one summary every 10 minutes, unless the error matches this specific high priority pattern. That is the essence of ISA 18.2. It is about protecting the most limited resource in the entire system, the human's attention. We call this reducing the cognitive load.
It is funny how these industrial standards from the 1980s and 90s are so relevant to cloud-native developers today. It is all the same math. It is all about signal-to-noise ratio. Whether you are managing a nuclear reactor or a Shopify store, the principles of alerting don't change.
It really is. And there is one more pattern I want to mention that is absolutely critical for reliability, the heartbeat or the dead man's switch.
Ah, yes, the dog that didn't bark problem. This is where the silence is actually the most terrifying part.
Right. In a mission-critical system, the most dangerous failure is the one where the alerting system itself dies. If your server goes down, but your monitoring script also crashed, you will never get an alert. Everything looks fine on your dashboard because no new errors are coming in. You are essentially flying blind.
So you need a system where the absence of a signal is the alert.
Precisely. You have your automation send a heartbeat signal to a monitoring service every 60 seconds. This is just a tiny packet that says, I am alive. If that service doesn't hear from your automation for 70 seconds, it triggers the alert. This is how the red alert system and J alert ensure they are always ready. The sensors are constantly checking in. If a seismometer in rural Japan stops talking to the central hub, an engineer is dispatched immediately, because that silence is a critical failure. It means there is a hole in the detection net.
I use this for my home server setup, actually. I have a simple cron job that pings a service called health checks every few minutes. If my internet goes out or the server loses power, I get a notification on my phone through a different network path, usually cellular data. It is so simple to set up, but it provides so much peace of mind. It turns a passive monitoring system into an active one.
It is a fundamental pattern, and it leads into the idea of multi-channel fan-out. Think about Amber Alerts for missing children. They do not just send a cell broadcast. They push to the emergency alert system on television and radio, they update digital highway signs, and they hit third-party apps through various application programming interfaces. They are saturating every possible channel to ensure the message gets through.
It is about redundancy through diversity. If you only rely on one path, you have a single point of failure. If Slack is down, your alerting is down. If you are building a critical business automation, maybe your primary alert is Slack, but your secondary is a text message through Twilio, and your tertiary is an actual automated phone call. You want to use different underlying infrastructure for each path.
And that is exactly what the latest updates to the Integrated Public Alert and Warning System, or IPAWS, are pushing for. They recently introduced the Message Design Dashboard version 2.0, which helps emergency managers create these multi-channel messages more effectively. They are even looking at things like silent alerts, where a device might only vibrate in a specific pattern for certain types of low-level warnings to avoid causing a panic while still informing the user. It is about using the right channel for the right level of urgency.
That is interesting. It is almost like haptic feedback as a data channel. We are really seeing the alerting surface area expand into every corner of our lives. Even the regulators are getting involved. You mentioned something about the Financial Industry Regulatory Authority, or FINRA, earlier.
Yes, for 2025 and 2026, FINRA is putting a huge focus on artificial intelligence-driven surveillance and real-time reporting. They want broker-dealers to have alerting systems that can catch suspicious trading patterns as they happen, not days later during a manual audit. This is putting a ton of pressure on financial firms to build these kinds of high-speed, high-reliability pipelines we have been talking about. They are essentially building J-Alert for money laundering.
It feels like we are moving toward a world of continuous auditing, where the alerting system is basically a real-time reflection of the state of the entire world. But that brings us back to the human element. If everything is an alert, nothing is an alert. We are back to the problem of alert fatigue.
That is the ultimate danger. We can build the most incredible, multi-layered, XML-based cell broadcasting air-gapped systems in the world. But if the person at the end of the line has alert fatigue and just hits snooze without looking, the whole thing was for nothing. We saw this in the early days of industrial automation, where operators would literally put tape over the alarm lights because they were so annoying.
Which is why the design of the alert itself is so important. It needs to be clear, it needs to be actionable, and it needs to be rare enough that it actually commands attention. A good alert should tell you three things: what happened, why it matters, and what you need to do right now.
Well said. So, for our listeners who are builders, what are the big takeaways here? How do they take these red alert level concepts and apply them to their N8N workflows or their Python scripts?
I think the first one is, don't just notify, automate. If you can define the response to an alerting code, do it. Make the human notification the last step, not the first. If a server is down, restart it automatically and then send a message saying, I restarted the server because it was down.
Second, implement a heartbeat. If your automation is important, you should know when it stops running, not just when it throws an error. Use a dead man's switch. Silence is not always golden, sometimes it is a sign of a total system collapse.
Third, think about your fan out. Don't rely on a single service like Slack or Discord. If the message is critical, use at least two different delivery paths that use different underlying infrastructure. Think about the physical path of the data.
And finally, embrace the alarm rationalization mindset. Use shelving, use aggregation, and protect your own attention. If an alert isn't actionable, it shouldn't be an alert. It should be a log entry. Be ruthless with your notifications.
This has been a fascinating deep dive, Herman. It really makes me look at those sirens outside our window in a different light. It is not just a sound. It is the output of one of the most complex and resilient engineering feats in history. It is a testament to what we can build when the stakes are as high as they can possibly get.
It really is. And if you want to dig deeper into the technical specifications we mentioned, like the Common Alerting Protocol version 1.2 or the ISA 18.2 standards, we will have links and further reading over at myweirdprompts.com. We have even included some sample XML payloads for those who want to see what a CAP message actually looks like.
We have a huge archive there of over 1,200 episodes, including some of the ones we mentioned today, like episode 745 on cell broadcast and episode 888 on the engineering of sirens. You can search the whole archive right there on the site. It is a great resource for anyone looking to level up their infrastructure knowledge.
And hey, if you are finding these deep dives useful, it would mean a lot if you could leave us a review on Spotify or wherever you get your podcasts. It really helps the show reach more people who are interested in this kind of technical exploration. We are a small team, and your support keeps us going.
Definitely. You can also join our Telegram channel. Just search for My Weird Prompts to get a notification every time a new episode drops. We love hearing from you guys, so if you have a weird prompt of your own about alerting or any other technical system, there is a contact form on the website.
Thanks again to Daniel for sending this one in. It was a blast to break down. It is rare that we get to talk about something that is so relevant to both our daily lives here and our professional work as engineers.
Until next time, I am Korn.
And I am Herman Poppleberry. Thanks for listening to My Weird Prompts.
We'll see you in the next one. Stay curious, and maybe check your heartbeat monitors today.
Good advice. Goodbye, everyone.
Cheers!
Talk soon.
I was just thinking, Herman, about that April 2025 market event you mentioned. It really was the first time we saw AI-driven surveillance and automated circuit breakers interact at that scale. It was like watching a digital immune system kick in.
It was a watershed moment. The speed at which the systems identified the anomaly and triggered the Rule 80B halt was incredible. It probably saved billions in irrational sell-offs. It showed that we can actually build stability into these incredibly volatile systems if we get the alerting right.
It makes you wonder what the next step is. Maybe AI that doesn't just halt the market, but actually starts providing liquidity in a calibrated way to counter the panic. An active circuit breaker instead of a passive one.
That is the active intervention model. It is controversial, but in terms of alerting architecture, it is just adding another automated branch to the pipeline. It is the logical conclusion of machine-to-machine automation.
The future is definitely going to be fast.
Faster than a P-wave, that is for sure.
Alright, let us wrap it up for real this time.
See you later.
Bye.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, my weird prompts.